Hello again. Guess who's back? It's me. I'm here to talk to you about 2.8. Okay, so once again, things are a little shifted around. Just to recap, I already sent out a video on 2.7. This one, we're going to talk about our 2.8 notes. And I also want you to take a look at our checkpoint 2 and test review once we've completed 2.8, because once we have done 2.8, we are done with the chapter. Okay, so just a little reminder, if you don't have your 2.8 notes, you can get them from our Canvas course page. You can download the blank copy. Also, I think the completed copy was set not to be available until next week. I went ahead and changed that so the completed copy is available tomorrow on the 13th, okay, for 2.8. So, let's recap. Sometime today, which is the 12th, the actual snow day, I would like you to try to submit the 2.8 pre-class. Honestly, though, if it's sometime after today, it's not the end of the world, just things are weird. So just turn it in as soon as you can, please, to get that out of the way. Okay. Now, I am tentatively saying that the optional study session for test 1 is still going to be going on tomorrow, which is Thursday from 2 to 3:30. If you're able to pop in, great. If not, we will have probably just like an alternate study session just for our class on Monday after class. So I will send a separate announcement out about that once we find out for sure what tomorrow's schedule is like for the college being open. Okay, so then on Monday, we have the 2.7, 2.8, and homeworks and the checkpoint 2. Tuesday is the test review, and then the test is on Wednesday. So let's dive right in. We're going to go ahead and take a look at the 2.8 notes, and we'll knock those out. Just a little reminder, if you want to take a look at, again, your checkpoint 2, like problem 1 really is from 2.5. So we definitely can do that. Problem 2 are all different variations of problems from 2.6. So you can also, again, get help from me in my office hours or test reviews, right? Problem 3 is really set up to be from 2.7, okay, where you're asked to find the derivative using the limit definition of the derivative. And then lastly, this last problem with the graph is really the only question on the checkpoint from 2.8. Okay, so we're definitely going to practice some similar ones like that in the notes. So I do want you to do as much as you can in that checkpoint and get help from me online or in my office hours. Because again, ideally I would love to see everyone have 100% on the checkpoints, because you can get help from me. You can get help from our tutors, whether it be in person or online, SI, all those things. Okay, taking a look at your test review, I have it broken up by example. Okay, by different sections rather, sorry. So we have like 2.1, there's one question, right? 2.2 and 2.3 have some more where it's like a mix of like graphs, right? And then finding it either algebraically or analytically or Lord above, squeeze theorem, 2.4 is everyone's favorite section where we define the precise definition, but they should all look very similar to things we've seen before. And that's going to be the same for the test. All these questions are going to be very similar to this level of difficulty, the ones that you're going to find on the checkpoints, on the quiz, on our actual mixed practice. Those are all great things to do. 2.5 is about continuity and the intermediate value theorem. 2.6 is questions from limits at infinity, more of that. 2.7 again is the derivative at a certain value. And then here's 2.8. This is where we're at. Okay. So 2.8 has a few questions on the review. So besides what we're going to talk about now, you could do 99, well, not 99%, but a lot of your checkpoint and review as well. Okay, so let's go ahead and dive right in. I'm going to try to keep this snappy, but Okay, so hopefully you want to go ahead and turn in the 2.8 pre-class notes. It just talks about some vocabulary words. So remember, derivative was a word they dropped on us last time. Now they take it a step further in 2.8, and they're like, okay, we're not just talking about the derivative at a point. We're trying to figure out where it's differentiable everywhere. Is it differentiable in its whole domain? Or are there some weird domain restrictions? And then they bust out the second derivative. So that's exciting, and then Leibniz notation notation, they talk about that as well. And pretty much just like we saw f prime of x, and we often use that, but we also, if the equation says like y equals, then we're going to say use Leibniz notation, which hopefully again you feel comfortable with in the text. But just a little note that in Leibniz notation is when it looks like this, dy over dx. So that's just what I'm looking for here. Then give your best shot, okay, to these. I want you to use your textbook to try to look at example 1, figure 1, and they solve a similar problem. And then I ask you to try it as well. But spoiler alert, we will pretty much be doing that as well. And then lastly, that there's some situations they talk about where the derivative doesn't exist, aka where it's not differentiable at that point. And then I asked you just to sketch some examples of those. So if you need any help on that, let me know. Okay, so we're gonna go ahead and dive right into these examples here. So for example 1, you'll see a and b here. It says, given the graph of y equals f of x, sketch the graph of the derivative next to it. Label each graph appropriately. So that is very similar to what I'm asking you to try, basing off of your just giving it a try in the pre-class. And we'll practice it a little bit. Again, there's one like this on the checkpoint if you need help. And then also there's some on the test review. Okay, so these first two, for instance, let's look at them. Okay, so this is the graph. This is nice. This is actually just a line, right? And so what the main idea here, I feel like, is that on each of anywhere on this graph, at any of the x values on here, whatever the slope is at each of those points is going to then become the y coordinate for our derivative graph. Right? So if this is the original graph, they give you the original graph, we could pick points, any points we want, really. And that's, I feel like, where it gets a little weird. You pick any points you want and figure out what does it look like. And it's just going to be a rough sketch for some of these. What does it look like the slope is at each of those points? Whatever that slope is becomes the y output on its derivative graph. Okay, so it's where sometimes it gets a little weird, just because we're kind of eyeballing it, sort of like we maybe sometimes try to do like in 2-1, you're like, ugh. So the good thing about this first one is it's just a line, right? It isn't curved. There's no changes in the slope. The slope is the same everywhere. It's a line, right? And so we could just focus on any of these points. I'll just focus on this point at -2. Okay, it looks like at -2, it looks like the y value is 4, and it looks like, again, this is just a line. So even if I try to like sketch a line, it would be this line, and it looks like the slope is about -2, I think, right? And here, when x is -1, it's also -2. Sometimes it helps people when they get more complicated to make a little table, and I think that's what we asked you to do on the checkpoint. We're like, okay, pick an x value, -2. Okay, what is the slope at -2? -2. You could pick another point. Maybe I'll pick 0. Okay, when x is 0, what's the slope? -2, right? And then when these keep going, then I'll say 2. When x is 2, what's the slope? Also -2, right? So when we are sketching our derivative graphs, like they ask us to do here, just keep in mind, we find out, if possible, what the slope is based like visually, right? And then that becomes whatever the slopes are, those are the y value, those are the y coordinates of our derivative graph. So for this graph, everywhere, okay, so like -2, again, the slope was -2, 0 was -2, 2 was -2. And no matter where, because it was a line for my first one, the slope is just at -2. And I'll do another example with you from the mixed practice just to kind of make sure we're all good besides these two here. Okay, so this would be an example of the derivative graph based off of my original graph. And hopefully it kind of makes sense because this is just a line. So essentially a line is like the first type of function we really learn where it's like, this is the slope, right? We're just finding we're pretending like we could draw like lines on on all of my curves, the slope, the derivative here never changes. The derivative is just a constant value. The derivative really for this whole graph, we could kind of see, hopefully maybe it makes sense, is like y equals -2, you know, or f prime equals -2, f of x equals -2, because it is a line. Again, a lot of them are more complicated. So we're just going to kind of, it's just the ideas we're sort of getting out here. Okay, let's take a look at the next one here. So you're like, okay, absolute value. That's nice. You know, we talked about absolute value a few different times in this class, and each time we talk about it, really, we've sort of actually broken it down into more of like a piecewise equation, right? Which is something that I think I probably saw at some point in time, but before calculus, I never really always correlated absolute value function with a piecewise function. But that's how we're going to want to think about it, because really what's happening is it's a line. There are two different lines, right? There's a rule that it follows when x is less than 2, in this case, because this is where like the corner is, right? And then there's a different rule it follows when x is greater than 2. Sometimes we would maybe focus on like, what is the limit as x approaches 2? And be like, oh, is it the same from the left and the right, right? So this is continuous, but hopefully it will get a chance to show you why technically, if you were to look at this absolute value graph, you could say that it's not differentiable at x equals 2, right? It is continuous. Again, there's no break in the graph. But we'll see, hopefully, when we look at the derivative graph, why sometimes they might say, why they would ask you, is it different? Where is this not differentiable? Kind of like, where is it not continuous? And you would say at x equals 2. Okay, so before 2, right? It follows one of these lines. It follows, we'll say this guy right here, we'll focus on what is this doing on the x values to the left of 2. So again, you can sort of pick some x values out, any x values. I usually just pick out ones that look nice. This one's pretty nice because I can sort of see they have pretty clear x and y points. There's no weird stuff. And it looks like the slope here is -1. Okay, so what this means is everywhere up until 2, right? The slope is going to be, oops, I missed -1. I'm sorry, -1, right? That is the slope of this line. So that is going to become my y coordinates, right, on my derivative graph. So just a reminder, whatever you have for your values of your derivatives, like whatever the magnitude of that is, that becomes your y coordinate of your derivative graph. Okay, so that's nice. But then after 2, if we look at it, it's not doing that, right? The slope is not 1. It looks like from all of my other x values, the slope is not -1, it's +1. So we make this huge jump. And again, this is where it looks very much like a piecewise function, to 1. And so whenever we talk about, again, this in pre-class, they mentioned differentiable, and they said, like, what are some examples of graphs that are not differentiable? This is a big one. Okay, this is technically has a corner. They also sometimes refer to them as cusps. Okay, so if you see a corner or a cusp, it's not differentiable at that point. Okay, and because it's because of this, because if you actually look at the derivative graph, the derivative graph is not continuous, right? The limit as x approaches a on the derivative graph would not exist, right? The left-hand limit is not equal to the right-hand limit. The limit, oh dear Lord, I just realized I did this at 1 instead of at 2. Okay, I don't know if anyone spotted that from back home. I'm sorry, guys. This is why if I'm in person, I feel like you guys would have caught this earlier for me. Sorry. But okay, I kept messing up. First, I said the y value was -2. And now I mixed up where the x value changes. I'm so sorry. Okay, so let's just recap what I did wrong there. I mixed up my 2's and my 1. So the slope for this graph was -1 when x is less than 2. I had it off on here. And then when x is greater than 2, it's at +1. So like, what's going on at 2? Yeah, it's just 2. It's not, we can't do that. We can't be at 2 places at once. Okay, so hopefully that kind of makes sense. Let me see real quick. I know I'm kind of jumping around. I'm going to go ahead and use this mixed practice as one that we're going to do together. Just one more, because those last two, those are both lines. And so when we do them and they're not lines, it can be a little bit different. Okay, so This one, if you look at the graph, sometimes I'm just like, what kind of graph I got here? It looks like a cubic function, right? And so they, instead of saying like, just pick some points, I tried to help out a little bit and say like, okay, let's focus on these certain X values. When X is -2, what does it look like the slope is? When X is -1, what would you guess the slope to be? When X is 0, what do you think the slope of that tangent line would be? When X equals 1, and then X equals 2 isn't even really on this graph, but we could see that like it does look like it's pretty symmetric in terms of like on the left and the right. So we'll talk about that when we get to it. And again, the ones we just saw, those were straight up lines. It was absolute value, and then it was just like a line. And so for those, the derivatives were always the same, and it was pretty clear. You could just like count down and over, count down and over. This one, when they get curvy, is where I wanted to make sure we had at least one example to give it a try. Okay, so the problem is again that we have to try to guess, right? What is the slope here at this point? Let's focus on first when X is -2. And there could be it could be different, right? We sort of talked about this a little bit in the beginning of class, like, I don't know, you know what you really, what I would recommend you do, and I have a marker pen like on the computer. It's probably not going to be great. Um, so I'm just gonna, I'm gonna try my best. But ooh, that I already don't feel great about that. But pretty much like I'm just gonna go ahead and draw a line up this way. I kind of went off a little bit on the rails to underneath of it. So let me try that again. I think I keep doing that. Okay. This is like my really not great. So whatever yours is probably looks better. So that, you can feel good about that. This is my rough tangent line that I'm just trying to draw like the exact steepness of at -2, which again, that looks like really bad, but it doesn't really matter because all I'm doing is I'm just sketching this so I can get a rough idea of what I think that line of the slope of this line would be. Okay, and again, this is why it's a little harder for these where it's curvy, because in the last one, it was a line. So we could just count the numbers up, rise over run. We have to actually sketch a possible tangent line to then use rise over run. And Lord knows, sometimes it comes out to be an exact number, sometimes it doesn't. We'll just see, we'll see what happens. So I went ahead and drew this line. Now you can draw this line farther up, you know what I mean, if you'd like to. Oh, I don't know if I should, because as you can see, I can't, I'm not good with the straight line on the, it's not good. But okay, I'm just gonna stop before before I make it any worse. We could extend it out, and really we're just going to get a rough estimate of what we think the slope is. So, this one's not the best. I'd say this is sometimes how I do it. First, I look to see if there's any clear points that it goes through. Now, I know I have this point here, -2, 3. I wouldn't say I have another super clear point on here. It just like if I follow this line, like it's kind of close here, but like not exactly, and then I kind of missed it here. But you can sort of like pretend if you want to. Again, I was just drawing a terrible line. Like it mostly would be like this, right? The slope between these points here. And so if I calculate the slope that way, just trying to find clear points, I'll go up 1, 2, 3, 4, 5 over 1. So like maybe like 5-ish, Sometimes if I really can't get a clear point, I eyeball and I'm like, okay, my one point like starts like here in the middle. Where am I like also like kind of close to the middle? Like I don't have a line, but I'm like, okay, it looks like I kind of went over 1. So let me just go ahead and count up the vertical change, and I'll count that as like a horizontal change of 1. And so I'll be like 1, 2, 3. Oh, it's also like about 5. So I feel like about 5 is like a fairly good estimate at -2. However, depending on how you drew your line, it could be anywhere, I'd say, from like 4 to 7. I think I would be acceptable. Because we're just guessing. We do not have the actual points. All right, I'm gonna do another one. And if you already feel comfortable, you can just fast forward as I go through this one. Okay, -1. Once again, I'm gonna try to draw. I'm gonna take one for the team and try to draw what I think the steepness is at -1. It's not Not great. I'll go ahead and try to extend it out this way first to the right-hand side. If I had a ruler, I would probably, in my actual paper, I would maybe just, bust that out and like try to line it up and kind of go that way. This is the best I have right now at -1. We're gonna go with this. Okay. So again, we're just trying to find out what is the slope you would guess of this point. So few different ways we could try, right? Again, you can try to just eyeball of like, if I extended this line all the way out, are there any points that I really go through that are like good, clear points? And I don't really actually have that many. I feel like I have maybe this one all the way up here and maybe this guy. So those are very far apart. But I could try to count those. I could say, okay, 1, 2, 3, ooh, 4, 5, 6, up 7, over 1, 2, 3, 4, 5, 6, up 7 over 6. That's a weird number. Or you could just, again, depending on where you kind of drew it, like 7 over 6 is like a little over 1, right? So I feel like in there, you could accept anywhere from like a slope of 1 to 1.5. Even like if you drew your line like a little steep, then maybe 2. It's totally up to you. Okay. And so again, I feel like that's where it gets weird. All right. I'm gonna do one more and then I feel like it's pretty symmetrical. So hopefully we're good from there. This is my favorite. This is usually actually where I start, but it's fine. At 0, it looks like the graph flattens out. So the slope there would be about 0. I should have started there, you know? And then just to kind of go through, it looks like, again, like at 1, if I was to try to draw the line, it's pretty close to what I had going on for my line at -1. So I'm just going to steal whatever I have for that one. I'm going to put that for 1. And then also I'm going to go ahead and make the guess that at 2, it's going to be about the same as what I had at -2, 5. And then I would take those points there, and remember, those now become our y values on my derivative graph. So this is no longer just the original function. This y-axis represents the derivative. Okay, or at least our rough estimate. So when it's at -2, for instance, I got 5, which may or may not be accurate, but it's close enough. Okay, and when x was -1, I got 7 over 6, which is like a little bit more than 1. So, it's good enough, as my husband says sometimes, good enough for government work. I don't really know if that's offensive, but I feel he works for the government, so I feel like it's okay for me to say that. I don't know if it's okay for me to say that, but anyways, okay. So this is kind of what this looks like. Okay, would be my rough sketch. Again, these values could be a little bit different. So if you need help with that, definitely come check in with me. We'll practice a little bit on Monday and go from there. Okay, all right. Now that we put that aside, we're going to go ahead and focus on this lovely scenario. It says to calculate the derivative and the domain of the derivative, I think is what they're referring to. The domain of f of x and the derivative of the domain of the derivative. Okay, and what does the domain restrictions tell you about the function and its derivative? Okay, so um, fine. Now, just a little comparison to 2.7. I know we already started out with some differences in terms of the graphs, but also something that is similar but different is here they don't give you an actual a value to focus on, right? They just say compute the derivative. So when they say the derivative and they don't give you a x value to plug in, our answer is going to be an equation, right? An equation that if I did plug in an x value at any of the points on the function, I would get out the slope of the tangent line. Right. And so we're taking it from, instead of just focusing on one point at a time of the derivative, thinking about the derivative as a whole and what it looks actually, we could actually, we can graph it sort of like they started us to do here. And we can just look at its own properties that way. Okay. So first things first, let's talk about the domain, I guess, of f of x, because it does ask for the domain of both, so we might as well start there. Okay, so I'm going to write d with a subscript of f to represent the derivative of the original function. Okay, and so we can look at this and be like, all right, we could say a bunch of things about this original function, right? But one thing that I can see is that x plus 1 cannot equal 0, x cannot equal -1, and then if we looked a little closer, be like, okay, is that a vertical asymptote or a hole? It's not a hole because there's nothing I can cancel out. So this is like a vertical asymptote, right? And so the domain, if I had to write it out, in interval notation, I could say is -infinity to -1, and -1 to infinity. Okay, so what is this going to tell us about the derivative function, right? I think, I'm just going to go out on a limb, but I'm pretty sure it's the domain is also going to be restricted on the derivative here, right? Because again, we're thinking about like, even if we thought about like a graph of an original and the derivative, um, how would we, represent an asymptote? It's if the original graph doesn't exist, the derivative's not going to exist there, right? So just sort of kind of touching on that idea. All right, let's find the actual derivative. Okay, so when we are talking about the derivative f prime at x, right? So there's no a here. There's no number. And so we'll say the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Okay, so same vibes as 2-7. The only thing is it's gonna be less numbers, okay? Because before on 2-7 we had like a was 2 or something, and everywhere we had an a, we plugged in 2. Here, it's just gonna be more broad. We're just gonna be keeping lots of x's and h's, kind of more similar, I feel like, to like the actual difference quotient most times is sort of where we wouldn't often have a number to plug in. Okay. So I still do like to sometimes go off on the side. On 2-7, I would say first, plug in A. Well, we don't really have an A, so I would usually just kind of jump to focusing on simplifying what f of x plus h is off on the side. Sometimes it's worse than others. This one there's not really a lot we can really do to simplify f of x plus h, but we'll just kind of go off on the side to do it anyways, just to say we did it. Okay, so on f of x plus h, I'll just label this side. Everywhere I see an x in f of x, I'm going to insert an x plus h. So then I'm left with x plus h divided by x plus h plus 1. Yikes. And we didn't even really know it in 2-7, but sometimes having some numbers really helped us out. There's not really a whole lot we can do here. There's nothing to be done. So I did that though, at least. And also I feel like it doesn't really make sense to go off and just rewrite f of x. Like in the last section, maybe be like f of 3, and we would plug in 3, but we don't have that. We just want to keep it as x. So I think that's about all. I'm going to go off on this side there. Okay, and then from there is when we're just going to go back to the original definition and substitute f of x plus h and f of x into my lovely derivative form. All right, so let's do this. So very similar to 7, just less numbers. Okay, so we're going to go ahead and say the limit as h approaches 0. Instead of f of x plus h, I'm going to rewrite this as x plus h divided by x plus h plus 1 minus f of x, which is x over x plus 1. On a little side note, I feel like it's a little aggressive for the first problem, but it's okay. If we can do the aggressive ones, the easier ones will hopefully be no problem. Because this is like kind of a gross complex fraction, but the same ideas are going to apply as to everything we've been doing so far, right? We then have to do some simplifying, depending on what we got, So if their f of x was originally a polynomial, I'd probably do some like, canceling of terms here. Since it's a complex fraction, I'm gonna have to simplify the complex fraction as we simplify complex fractions, right? If it was a radical, I would probably need to bust out my conjugate radical skills. So this is a complex fraction. So I just wrote simplify. Let's try to do that. So I have a complex fraction. Again, this is where in theory people could do 2 ways, but we're just going to do it the way that our textbook kind of likes to do it often, but I don't know. Won't say all the time because who knows. But I'm going to multiply by the least common denominator of my mini fractions. And the least common denominator of my little fractions is x plus 1 times and x plus h plus 1. Man, I don't think that came out right. So pretty much I have my denominators are my LCD. So we have x plus 1 times x plus h plus 1. I don't know. I think that worked a little better, but I don't know. Okay, so I'm going to go ahead and write my LCD so that I can then distribute. My denominator is going to stay ugly. And my numerator, hopefully a bunch of stuff cancels out for me. Okay, so for instance, in the numerator, again, if I was to distribute in my LCD in here, the first term is x plus h plus 1 is going to cancel out, right? And so we're left with x plus h times x plus 1. I'll deal with you later. Minus, in my second term, the x plus 1's cancel out. So I'm left with x times x plus h plus 1. Again, this is where it gets a little, this was an aggressive one to dive in, but we got this, okay? And so I think that's all we have left in my numerator, and in my denominator, I'm going to keep this as is. It's technically almost like already in factored form for us whenever we do this. So we're just going to leave that as is. Okay, I do have to do some tidying up in my numerator. So let's do that. So I'm going to go ahead and recopy this down. Again, don't forget to bring that limit part along the way. I feel like especially when it gets gross, it's the first thing to get forgotten, but we got it. Okay, and then we're going to go ahead and write x squared plus hx plus x plus h if I FOILed out x plus h times x plus 1. Not great, but it's fine. Now I'm going to go ahead and distribute in my negative x. Okay, so I'm going to say negative x squared minus hx minus x. Notice I could have also written 8xh. It's just like I usually will just like whatever I did in my first part. So I wrote hx on my first part. I'm going to try to keep it in that same order for my second piece so that I can look at them and realize like, oh, hx and hx, those are the same things. Sometimes our brains just don't recognize that if it was written as hx and xh, they're the same, but they are the same, right? They're all the same. Okie dokie. And then we got our lovely lovely denominator going on here. Okie dokie. I know. Again, I apologize. This is a bit aggressive, but we can do it. All right, so now things are going to go ahead and get eliminated. So we have the x squareds are going to be eliminated, the hx's are going to be eliminated, and the x is going to be eliminated. So things just got a lot better. And now I only have an h left in my numerator. So that's good. I can go ahead and cancel out the h's. I'll do that now as well. So I have one less line I have to write. Feel like, we've done enough here. Okay, I'm almost ready for the final piece here. Okay, so last but not least, I need to evaluate the limit, right? So I didn't even talk about it in the beginning because it was just so crazy. But if we would have originally tried to evaluate this at 0, we would have been again left with 0 over 0. But now that I canceled out that h all the way down here, once I've done all this pain and suffering, I can evaluate the limit. That's no problem. Okay, so I'll say, go ahead and say the derivative of f of x is 1 over x plus 1 times h is now just 0. So times x plus 1. Cool. I'm done. You could also, if you want to, you don't have to, you could rewrite this as 1 over x plus 1 squared, which is good, Okay. And then again, they asked us to find the domain of the derivative. And like spoiler alert, this is gonna be the same domain restrictions as our original, but let's just get it all out there. So here, x plus 1 cannot equal 0. So again, x cannot equal -1. Now we do you might be thinking, okay, actually, if I graphed this, I could say the limit of this does exist because they're both would be going to positive infinity versus in the first one, the vertical asymptotes would be the case where like one's going up and one's going down. But it's all good. Like it's not, that's just stuff to kind of think about if we can think about the graphs of the function and its derivative. And so what I'm just going to kind of add in here is that the domain of the derivative, okay, is where the function is differentiable. So if we have a domain restriction on the derivative, that means the function that we have is not differentiable there. So technically, we would say for this one, the domain or the original function x couldn't be -1. And we can also just add in here, since we took the derivative, we also know that it's not differentiable at -1, which, like, could have probably figured that out because there doesn't exist there, but here we are. All right, let's try another one, and then we'll do one word problem, and then I promise I'm gonna wrap it up. I know this is a lot here. So again, as long as you watch these and try them out, you can, hopefully be good to go. All right, now these are ones that are going to be much easier when we come back in chapter 3 and learn some real quick rules that, like, if some of you have already have some calculus experience, you might already know. Like, come on, do I really have to do this long way? And I'm like, oh, yeah, I was really sorry about that. Okay, so the first one, it just says, consider this function, x squared minus 3x, find the first derivative and the second derivative. Okay, so I can do that. All right, so the first derivative, again, the more we copy it, hopefully the better off we are. The limit as h approaches 0 of f of x plus h minus f of x, all divided by h. Okay, let's go off to the side and simplify f of x plus h. Okay, so in my original function, I'm going to take out the x and I'm going to insert an x plus h. And so I'm going to be left with x plus h squared minus 3 times x plus h, which would then be x squared plus 2hx plus h squared minus 3x minus 3h. And for minus f of x, again, if it was an actual number like 2.7, I would probably just make sure I have that written down there as well. But and 2.8, like, I have what f of x is. F of x is x squared minus 3x. However, I do want to make sure I don't screw up that this is a minus sign. That's a problem often for me and lots of students. So we'll be on the lookout for that, especially if it's a polynomial like we got here. Okay, so f of x plus h, I'm going to go ahead and rewrite what I have, which is not great. There's a lot of letters in 2.8, but it's okay. We just stay calm, and just keep going. Okay, and then I'm going to say minus f of x. So you have two choices here. You can say minus and then put this in parentheses and then rewrite this whole thing with the negative distributed. Or if you're like me and you're like, oh, I don't know, one less line just seems nice. I'm going to go ahead and distribute in the negative. Okay, so minus the quantity x squared minus 3x. If I distribute in that minus, is actually minus x squared plus 3x. And you'll know if you messed it up because I have to change the signs for everything to cancel out, which is going to happen next. But just in case, okay, all right. And this is all divided by h. So at least I didn't have to do anything with h, that's just hanging out. Okay, this is the satisfying part-ish. Okay, so the x squared and the negative x squared go away. Great. And I have negative 3x and positive 3x. So everything I'm left with does have an h, but it's a little bit more than what we sort of saw again in 2.7, where it was just like maybe like one number and an h. It's a little bit more than that because it's going to be like an equation. Okay, so I'm going to factor out an h of what I have left. So I pulled out an h, and so I'm left with 2x plus h minus 3. If I take out the h from the h squared and also the negative 3h. And it's all divided by h. Okay, all right. And so we do that so that we can cancel out our h's. But here again, I'm just going to go ahead and rewrite it so we're all on the same page. This would be 2x plus h minus 3, which I can go ahead and evaluate now. Good news. I can go ahead and plug in 0 for h, and I'm just left with 2x minus 3. Okay, so what this means, I just want to kind of make sure this makes sense, is I have this derivative. I have the original equation was x squared minus 3x. And then, oh gosh, I'm sorry. The original equation is x squared minus 3x. My derivative equation is 2x minus 3. I'm also kind of like, I feel like, I would probably, if I was a student, I'd probably at this point need to like take a little break because I know 2.7 and 2.8 are a lot, and I'm just trying to knock them all out with videos right now. Okay, so if I was to think about this on like a graph, right? I just want to kind of make sure this makes sense because we have this like graphing portion, and then all of a sudden we sort of switch gears to this really painful difference quotient stuff, Okay, so this is my equation, x squared minus 3x. I just went ahead and found that the derivative for this graph is 2x minus 3. So what I could have maybe been given as like one of the problems we saw in the beginning was like, oh, take this graph and try to, sketch its derivative. Like, how would I do that, right? Like, you're like, oh, like here, the derivative could be, I could maybe draw some lines. It looks like it's, I don't know, like -3. Well, now we can actually go in, we could plug in 0 into this derivative equation, and we would get -3. So we would know that exactly the y coordinate of my derivative is -3, right? I could do the same thing at like 3, I would be like, oh, what's the derivative here? I could try to sketch a line. You saw how I suffered there. But now I actually have the derivative equation. I can just plug in 3 here. And so it would be like 6 minus 3, 3, right? And so that's telling me my derivative here is actually at the point 3. Here it is. There, where are you? 3, 3. It's somewhere there. It's like right there. Sometimes I'm struggling with Desmos today, but it's okay. Why would I want all these other points? Come on, Desmos, get it together. There we go. 3, 3. Okay. So everything that we sort of did where we were sketching these derivative graphs, if we had the actual original equation, we could find the derivative now. It might suck, but we could do it. Okay, so this question also asked us to find the second derivative because that's how nice they are. So we can do that. That's just the derivative of the first derivative. No big deal. No big deal. Okay, so let's go off and talk about the second derivative now. I'm gonna really just treat my derivative that I just found as like the original function. Okay, and so let's just write it one more time. I'm gonna go ahead and say f prime of x is going to equal same dang thing. It's not as bad. It's gonna get a little easier, I think, for this one, but I know. Okay, so technically what we're doing is we're taking that derivative and the first derivative and plugging in again x plus h minus the derivative at x, and then it's all divided by h. So let me just go off to the side. At least I don't have to FOIL anything, and talk about what happens when I plug in x plus h into the derivative equation, right? So I take out x and I put in x plus h minus 3. And so for this one, I'm just doing the whole process over again, really. It's quite annoying, I know. For those of you, again, who know the derivative rules, you're like, really? Is this really what I have to do? I'm so sorry. But it is just for this section. And then after that, we're good to go. All right, so the derivative, if the second derivative is going to be the limit as h approaches 0 of f prime of x plus h. Okay. I went off and found that was 2x plus 2h minus 3, much better than what we had up here, so that's something. And then minus f of x, again, I don't really want to have to rewrite this another time. I don't even really have space for it. So I'm going to go ahead and distribute in the negative here carefully. So this would become negative 2x plus 3, and then it's all divided by h. Okay, so I promise you this one's a little bit better because now there's not a whole lot we have to worry about. The 2 x's cancel out, the -3 cancels out with the +3, and all we're left with is 2h over h, which thankfully there's a God, because now that's just 2, okay? And so what we're saying really actually is that the equation for the second derivative is just 2. And that does kind of tie back, to those questions that we had before, where if you were asked to take a line and sketch the derivative graph, the one we saw, it was just a flat line, right? The slope of 2x minus 3 is always 2. So like we didn't really have to go through that whole thing just to know that that slope is 2. But we did. Okay, we did it. All right, last one we're going to do here. We have this lovely particle equation. The good news is I'm not going to really make you do this all over again, because this is actually sneakily the same equation as what we had up above. It's just that instead of x's, we have t's. Okay, so when we are actually finding these, you would do it the same way. It's just that, we've suffered enough. So I want to make sure we just sort of can knock this out real quick, quicker than the other ones. We did an example of one that's a complex fraction, and we have this one here. It's like a polynomial. You could do a radical just using the same skills that we did in 2-7. Like, you got this, okay? So since a particle is moving along a straight line with this position, it's another random particle. And then it says, functions. Find the velocity function, the acceleration function, and the jerk function. And then it says, using the functions, find the velocity, acceleration, and jerk at time t equals 2. Be sure to label your answers with correct units. So this is where I feel like it gets kind of fun, which I feel like when people say it's fun, it's like not as fun. But here we are. Okay, so good news. All of those things that we've been learning, we can apply directly to these application problems, especially physics. It goes hand in hand, right? So they usually use S for the position. And just like we sort of saw in 2-7, right? The only difference is in 2-7, we were only focusing at one point. I think it was like t equals 3 in the notes. And so when we found the equations, we didn't find the derivative, like what our equation wasn't 2x minus 3. It was like f prime of 3. And so we were always just focusing on one particular point in time. Now we can broaden this to like anything, any time values, right? Well, when time is positive, because who knows what happens if you try to negate time there. Okay, so the velocity is just the first derivative, right, of the position. So that's good, and they usually will just refer to it as like v of t. So cool. Acceleration is really just the first derivative of the position. I'm sorry, the first derivative of the velocity. Dear Lord. Okay, so that is really actually like the second derivative of the velocity. Oh my gosh, I keep mixing up my words. I'm so sorry. Let me say this one more time because I think I'm just getting tired. My dogs are looking at me and whining. Okay. Let's recap. Okay, so we have our position, and this is how I kind of think about it typically. I think if I'm more, I'm a visual person. So we have our position, right? If we take the derivative, this is taking the derivative, we end up at the velocity, right? And then if we take the derivative of the velocity, we end up at acceleration, right? And then lo and behold, when you get like, bumper cars, you get hit by a car, you get like jerked around, because it's just such a, yeah, that is the rate of change of acceleration, right? Where it's like you're not only accelerating, but your acceleration is accelerating, and you're getting jerked around. So I feel like it kind of makes sense in terms of the word. And so last but not least, that would technically have been like the third derivative of position, which is if you have the velocity, the second derivative of velocity, which is the first derivative of acceleration, which is what we can go ahead and call J of t. Sure. Great. All right. So they just asked us, again, we're just using example 3 above because it's really the same equation. It's just instead of x's, I have t's, and instead of f's, I call it s. But we're just going to kind of use that work instead of having to do another one because they are quite excessive, but we do want to kind of get like the vibe of what we're doing with these word problems down, at least like the big ideas of like you can take the derivative of the position to get the velocity equation. You can take the velocity equation, you take the derivative of that to get the acceleration, take the derivative of the acceleration to get the jerk. We don't really do too much of jerk in this class, but I don't know, maybe you can let me know if you see that in your physics class at all. Okay, so using the example 3 above, right? That was up top there. Using example 3, look up what we just did. Okay, if you remember, as like a little spoiler, f of x was x squared minus 3x, and then the first derivative was 2x minus 3 when we found, and then we found the second derivative was 2. Okay, so we're going to use it, but instead we're just going to use our new notation. Okay, so for A, they want the velocity function. So remember, the velocity function is just the first derivative of the position. So the position, if we're rewriting our f of x and t, be t squared minus 3t, right? And the velocity equation would be 2t minus 3, okay? And then the acceleration equation would be just 2. Now, we didn't really calculate the jerk equation, right? We didn't find the third derivative originally, but hopefully this kind of makes sense. If we have just like a flat line, right, at 2, like a horizontal line, what's the slope of that line, right? Without having to pretend to have to worry about the definition. The slope of a flat line is just 0, right? So I hope it kind of makes sense. Again, if we wanted to, we could just sort of through a little bit of the definition, but if you ever have just like a flat horizontal line, the rate of change of that is just 0. Okay, and then using that, they want to know all of the things. They want to know the velocity, acceleration, and jerk at times t equals 2. So we can do that real simple, really, and we'll be careful about units. So the velocity at 2 would be, let's see, 2 times 2 minus 3. I think that would just be 1 meters per second. Last class, I think they're like, oh, is it moving forwards or backwards? So it's technically moving forward. I'll just kind of label it. I don't think they even asked that, but I just wanted to kind of add that in there. It's moving forward. And A of 2 is 2. So also the acceleration on it is positive. So it's moving forwards and it's accelerating positive. So it's like speeding up, right? And we'll add that in later, but the whole speeding up and slowing down, we don't have to do that right now. And then lastly, the jerk, we don't have any jerk in any of this. There's nothing, there's no other stuff happening. So I'm gonna go ahead and say that's 0 meters per second cubed. Because again, it is all just like the rate of change of the rate of change. So we're talking about like, how does the meters per second change per second? That's why it's meters per second squared, right? And then how does the acceleration change per second? That's why it's like 0 meters per second cubed. All right, once again, longer-winded than I intended, but I hope that helps. Again, we are going to use a lot of about half the class on Monday to kind of review, kind of give, depending on if you bring me questions, great. If not, I'll probably just give you a little bit of the mixed practice to ask you to try. And then unfortunately, we do have to move to 3.1. So just to recap what we want to do, we are not sure yet. We might have the test study session tomorrow if you can come from 2 to 3:30. Either way, we'll probably have just, please, if you can stay after class on Monday, please plan to do that to get some help about that. Okay, so today, make sure you get your 2.8 pre-class in. And the 2.7 and 2.8 web assignment are due on Monday, as well as the checkpoint 2, and then the test review is due Tuesday. You're not going to have enough time to do 2.7, 2.8, checkpoint 2, and test review all between Monday and Tuesday. So you're definitely going to want to get a good jump on that this weekend. So please let me know what you can help with. I'm going to ask you to make up for our quote attendance, just to comment on the announcement with questions, comments, concerns, all that stuff. Those instructions will be on there. All right. Good luck out there, everybody. Stay safe. Keep me posted. Thank you.